Hello, I am Joshua Mitchell with Middlesex University, London. In this video, I'm going to be demonstrating my submission for the LabVIEW simulation of a generic serial manipulator as part of PD3442 Mobile Robots and Manipulators with Dr. Aleksander Zivanovic. For this video, I'm effectively going to start at the end product of the project, working with this tab. For the project, we had to design the Zivanovic-Hartenberg parameters of a robot that was capable of mounting on a turtle bot and reaching to the 4 positions that I'm showing you now. The only specification given for these positions was the height, which is why I'm only showing the Z coordinate as required at 6 for 0.2 and 0 meters, sorry, 0.6 and 0.4 from the floor. Now in my robot, the top of the turtle bot would be here. This is the floor, and this is not a link, it's just an offset. The link would come out over here. So I've also animated these as well as had the 4 positions individually. The reason for the animation coming to the side was not required. As I said, only the Z was required, the height. But I did that because as I was animating, I thought it sort of looked like it was picking something off of maybe a conveyor belt and placed it onto various shelves. So that's why I just had the conveyor belt coming in this side and the shelves over here, just because I could. I'm well aware that this is not an optimized robot. There's a lot of links that aren't needed. And because only the height is required, I don't need this rotation at the bottom at all, which would obviously reduce 2 because it would reduce that one and that one at the top. And these 2 joints here could be 1, so I could bring this robot down to a 4 or possibly even a 3R manipulator rather than a 6. But the amount of bits we had were not specified. It was just for a generic serial manipulator. So moving on, while I have these, note the steps and cycle speed. I'll be coming back to those later in the video when I show you the code. But to show you the effects they have, if I bring the steps down, it will affect how much the trajectory plots. And so you can see if I bring it down perhaps even more, let's say 5, make it very clear, it jumps a lot quicker. And the cycle speed is how long between each trajectory. So if I bring that location, so if I bring that up, you can see it basically slows down the robot. So I've got 50 and 20 as default just because it's a fairly nice speed. And you can still observe the behavior. I also have the home location, which is just straight up. During the play all, it shows you what cycle it's currently on, and it shows you the live feed of the height. So again, I can prove there that it is meeting the specification going to the desired heights. Down here, I have the full table of my Zivanovic-Hartenberg parameters. So the rotation is undefined because they're revolute joints, obviously. So in order to get to these locations that it was moving to, I used my inverse kinematics. And to validate that, in turn, I used forward kinematics. So for these, I can do radians or degrees of where it needs to go. It's a little bit skew-if at the moment, but let's just say there for now. And then, so obviously that was my forward kinematics. So I got both radians and degrees. Whoops. And I can also get the joint positions through jogging with my inverse kinematics, the X there, Z, and Y. You can't see the Y very clearly. Let me rotate it around. There's the Y rotating around. And then that is output in these positions, which is what I then use to design these. But yeah, not entirely sure, but we'll carry on. So that's basically the project summed up. If I now show you the code. So in the first sequence here, I have a bunch of positions defined. These are the joint positions I was just talking about that define the preset positions to go to. So we have the home, the floor, floor approach, low shelf, low approach, carry on. This box here is my DH parameters, same as what were displayed on the front screen, which are then fed into the initialized generic serial arm and then fed into initialized plot. Pardon me. I also have an initial joint position for the forward kinematics, which is when you first open it, and I also force the tab control onto forward kinematics at first. So after that, we take the length of this array, which I could have made a constant, but in case I wanted to add or remove positions, it would just adapt. Is fed into this case select. We'll come back to why that's used a little bit later. But for the forward kinematics, if the only one that's actually passed in is the error code. So get into it. For the forward kinematics, we take the joint positions and either radians or degrees, depending on the angle units. Pass that through into the forward kinematics module, VI, which then gives us the computed transform, which is also fed down here into the shift register. And I also separate the X, Y, and Z coordinates out of here. They are then times by this, which is just to use with the jogging buttons that you just saw. It's basically the resolution of how much they affect it when they're held down. So that's more or less it for the forward kinematics. It computes based on joint positions, and they also feed into the plot and then 3D picture. This variable here is a global variable used for another VI, which was linking this project to a SolidWorks model to validate the simulation. I'm hoping to go through that in another video, and also how to set up the communication between LabVIEW and SolidWorks. So I'm not going to be explaining that in this video because it wasn't part of the submission, but watch out on my channel in case I upload that later. Moving on to, let's say, the inverse kinematics next. Down here is my jogging functions. So it takes the shift register value. In here, all that happens is it looks at basically, is it within range of the shift register, and then either adds or decrements out. So that's that. That value is then passed through into these three, which take the computed transform matrix from the forward kinematics, inserts these into the X, Y, and Z coordinates, Y, Z, at the end of the transform, which is then fed into the inverse kinematics. I'm using a mask on the inverse kinematics so that it's not going to try and change the orientation of the end effector. I found that when it was able to change the orientation of the end effector, the inverse kinematics would not be able to converge to a solution, and it kept giving me errors. So that is definitely a limitation of this project, that you have to keep the end effector in the same orientation. That block then in turn outputs the joint positions and updates the plot and sends it to the 3D picture. If you keep it in here, it will then do the same, and that's how it will run through with the shift register, and that's how the jogging controls work. I could have just used sliders or something with the jogging controls, but having looked at interfaces for the ABB, the 120 and the UR5 robots that we have at university, I found that they're more often buttons, so I just tried to follow that sort of convention, if you will. So the most complicated part of this case select, sorry, I should have mentioned this case select is just coming from which tab you're on under the kinematics mode. That's fairly obvious, I would hope. So moving on to the last tab, probably the most complicated, well, without doubt, most complicated, it's preset positions. So inside of here, we have an event structure, which handles which of the buttons you press, so the home, top shelf, mid shelf, low shelf, floor, and play all, which is another level of complicated. So we'll start with, let's say, the top shelf. They will be the same, effectively. We have the plotting trajectory sub-VI here, which takes the current joint positions from the shift register as its start joint positions, and it takes this constant here as the end joint positions. These are the constants I was talking about previously which I got from using my inverse kinematics jogging to set it to a certain position. I then just wrote them on paper and then rewrote them in here. So anyway, this then computes the amount of steps, which I showed you on the front panel, how that affects it, and will output here the interpolated trajectory positions. I could have used the Cartesian trajectory if I wasn't rotating, if I was to only use the X and Z coordinates, but because I had that rotate in there at the base, I had to use the normal trajectory. Anyway, that then feeds into a for loop, which runs through the same amount of times as the steps, and auto-indexes the data here, which is then broken up into the individual joint positions and fed into the plot to update the 3D picture, which is how it's animated, because it's every position through however many steps, and also into some kinematics here, which forward kinematics, which outputs my transform, which I then index and get my Z coordinate back out of it, which is how I'm updating that. So these two are local variables, so they will be updated every time through the for loop, not just when it outputs the final thing here. The cycle speed, again, is just a delay, so that's affecting the speed the robot will move at. So as you can see, if I go through, mid shelf is pretty much the same, low shelf is the same, and so is the floor and the home. The only difference is the constant to use here. The only one that is considerably different is the play all, but it's not too much more complicated. All it has is the extra layer of for loop here, which is auto-indexing all the values here. So this is effectively cycling through the positions in the order defined here. So it goes home, and then it goes to floor approach, then floor approach, etc., etc., etc. So these come through, they are auto-indexed into the trajectory as the end position, and the start position comes from the previous value. So this is still taking a constant, but rather than at the top here, it's cycling through all of these each time through the for loop. That then will run into this for loop, which is the same as I've explained previously, with the Z and the output and the 3D picture output. This again is to do with the SolidWorks, which I'm not going to go into in this video. And that's all. This is the cycle as well I mentioned in the front panel. It's just coming from the iteration count. So after it runs through whichever of these K-selects you're currently selected on, obviously it will output the 3D picture, the joint positions, they get cycled around, the X, Y, and Z and transform and the whole transform. And then after that, we just have the error out, stop, and error handle. So that is that. Thank you very much for watching.